Good morning. Let us continue our lectures devoted to probability distributions in infinitely dimensional spaces. And today we continue discussing of the criteria of weak convergence in abstract spaces and in application to weak convergence of probability measures in infinitely dimensional spaces. Let me recall you what you did last time. We considered arbitrary complete separable metric space and we were able to prove the following conditions of weak compactness. Namely, it occurs that if we have the family of probability measures, for example, mu alpha, X. It means on the Borel sigma field of X. Then it is weakly compact if and only if then this family appears to be weakly compact if and only if weakly compact if and only if for all epsilon greater than 0 there exists k epsilon compact set such that if with respect to the indices mu alpha from k epsilon is greater or equal than 1 minus epsilon. So up to the value epsilon, our measures are concentrated on this compact. It was named, this statement was named Prokhorov theorem due to Yuri Vasilievich Prokhorov. And now our aim is to adapt this statement to the case when the abstract space X has a specific structure. Namely, we will consider two cases. One is when X is a separable Hilbert space, real separable Hilbert space. Another one when the space is C01, space of continuous functions with uniform norm. Let us start with the Hilbert case. So now I will suppose that our abstract metric space is a real separate Hilbert space H. Consider space H is a real separate Hilbert now maybe we understand that concretization of the weak convergence will consist of using criteria of compactness of in our Hilbert space. Let me recall that if we have A, which is closed subset of H, then we know that A is compact if and only if only A is bounded and for arbitrary En, this is also normal basis H. We have the following relationship. Sup over X belong to A. The sum from K equal M X in K square tends to 0 when M tends to. So the series which define the norms of elements of X by the Parseval identity with respect to this orthonormal basis must converge uniformly. And this uniform convergence must hold for arbitrary orthonormal basis. This is characterization of compacts which we already know. So now we will adapt this. We will adapt the criteria of weak convergence to the Hilbert valued case. Let's see. Here is this condition, and it means that I can, for any epsilon greater than 0, I can find such n 0 that this supremo, let me do it. Okay, this supremo is less than epsilon. Is less than epsilon. So now let us came back to Prokhorov condition. We want to have a criteria for family of probability measures on our Hilbert space now to be weakly compact. So mu alpha is weakly compact compactness. If and only if rho epsilon greater than 0, there exists compact set K epsilon compact such that the infimum mu alpha from K epsilon is greater equal than 1 minus. Now recall that we have a condition on or description of K epsilon. So let us take now arbitrary orthonormal basis N is orthonormal basis. Then what we can see that we know that for the same epsilon which is greater than 0, maybe I will not write this epsilon again. Okay, we have this for the same epsilon. There exists n0 such that this sup over K epsilon of the norm x ek square is less than epsilon. Yeah. Now let us combine to this inequality, this one and this one. One can conclude that the infimum with respect to alpha belonging to our set of indices mu alpha from the such set of u that this sum from k equal n0 to infinity u ek square will be greater or equal than epsilon. Oh, excuse me. Maybe sup is less than I just use backward inequality in order to have more familiar to us relationship, because now we understand that we have a good condition for the compactness. It means that uniformly with respect to the index alpha, this remaining term of the Parseval series must go to zero in probability mu alpha. This is the necessary and sufficient condition for family mu alpha to be weakly compact. Let us write it again. We get the following statement: theorem mu alpha belong to the set of indices is weakly compact if and only if for arbitrary orthonormal basis En we have this is the first one condition. For every epsilon greater than 0, there exists and 0 such that and another one condition. You remember that we said that the compact set must satisfy not only this condition of Parseval series uniformly converged to the uniformly converged, but also it must be bounded. Yeah. So we have another one additional condition that the sup alpha mu alpha of such set of U, that norm of U is greater than R. So this is order of the ball of radius R equal to 0 when R tends to plus infinity. So we have such a good description for compact families of probability distributions in a Hilbert space, and these two conditions are absolutely clear. For example, if we have just finite dimensional case, then of course this first condition disappears, and only this one remains, and you already are familiar with this condition. At least in one-dimensional case, it means that our family have uniformly decreasing tails. Yeah. So this is condition from finite dimensional case. This is condition from infinite dimensional case, which allows us to catch our measures and do not allow them to go to infinity along the infinite number of gradients. So we have such two conditions, and by the way, here we can check interesting example. This example is related to the idea of application of characteristic function methods. You remember, in one-dimensional case, if dimension is equal to 1, if we have the convergence of characteristic functionals at any point, and n tends to infinity, then we have reconvergence. Yeah? Then we have reconvergence. Yes. Now let us then this equivalent to reconvergence. Tends to infinity. Yeah. Now let us consider infinitely dimensional case. Also Hilbert case, but infinitely dimensional. Now consider a Hilbert space such that this dimension is equal to plus 50, and consider the orthonormal basis. I recall that we consider only separable case. Orthonormal basis. And now let us define our measure mu n as follows. Mu n is a distribution of the following random element: psi1 e1 plus psi n en. Excuse me, e1, where psi n are independent side normal values. Okay. Then let's check the corresponding characteristic functionals. Phi n from the H, now characteristic functional, is element of is dependent on the element of H. Yes, this is expectation of E exponent. Here is imaginary unit, and here is psi1 E1 plus psi L En multiplied by H. Yeah. Due to the condition that psi n are identically distributed independent standard Gaussian limits, one can check that this is equal to the following: E minus 1/2 of excuse me, 1/2 of H E1 square minus 1/2 of H En square. Yes, it's evident. Then let us recall En is the orthonormal basis in our Hilbert space H. It means that H in N tends to 0 when N tends to infinity. So one can obtain that our characteristic functional goes to the power E minus 1/2 of H E1 squared when N tends to infinity. And evidently, this is characteristic function. Yes, it is. Let me denote it by phi of H, and it is easy to check that phi of H is the characteristic function of the distribution of very simple random element, mainly phi H is characteristic functional of the following random element psi1 E1, yeah, of distribution of, yeah. So we have here convergence of the distribution functionals in any vector H from our Hilbert space H. But let us check, do we satisfy conditions of the theorem which characterize the compactness or not? We have two conditions, and let us know that condition 2 is satisfied. Why? Because if we consider now probability, then the norm of psi1 E1 plus psi n En is greater or equal than r squared, then it is equal to this is just two-dimensional vector with standard Gaussian independent coordinates. So its square of the norm has exponential distribution. So it seems you can calculate constant, but this, I think that I am right. To plus infinity E minus R, small r, it goes to plus to 0 when r goes to 0. Yeah. Okay. So we have excuse me. So we have the following relationship, and it means that the second condition is satisfied. Now let us consider the first one. Take the same basis, then the sup over n greater than infinity probability that the sum from k equal maybe it's better to write here m k equal n0 to infinity. Here is psi1 E1 plus psi Ek square will be greater than epsilon is exactly equal to probability that they are equidistributed, so I will use psi1, that psi1 square is greater than epsilon, and it does not tend to 0 when n0 tends to plus 50. Yeah. So we have the following relation, which gives us a statement that the condition 1 is not satisfied. And this example shows us that in the infinite dimensional case, we face a new possibility for probability distributions. They can not only go to the infinity, but they also can run away through the dimensions of different coordinates. You see, exactly right there. This explains us why one cannot expect that we just have convergence of characteristic functionals to characteristic function in infinite dimensional case, and this will automatically gives us weak convergence. No, we have to add something. Conditions of weak compactness we need. So we need something which allows us to check conditions of Dorogovtsev A. Now let us consider next example when we can adapt Dorogovtsev A. This is space C01. Actually, maybe you understand general plan. When we want to get conditions for the weak compactness in some Banach space, we just have to describe compact sets in this space, and then say that our family of measures must be such that this condition will be satisfied uniformly in the sense of measure. Let me show you another example related to the space of continuous functions. Okay? So now, as our Banach space, we will consider space C01, and it is equipped with the uniform norm. I just will write this symbol of infinity one time to emphasize that we have here uniform norm, and further I will quit. We know that this is a real separate Banach space, and now we also can ask about the conditions of the weak compactness in this space. You remember that we start with the description of the compacts here because of Dorogovtsev A. So let us do the same. A will be closed, is closed subset, and what we have to add in order to make a compact. The first one, A must be bounded, for sure. A is bounded. And another one that came, another one condition that came from Ascolar-Celler theorem, which says us that it must be equicontinuous uniformly. Yeah? So the following must hold that sup over x belonging to A. Here is sup over distance t1 minus t2 is less than delta. Here is x t1 minus x t2 must go to 0 when delta tends to 0. This is the condition which describe the compacts in our space C01. Now let us try to adapt these conditions for the case when we have a family of measures, probability measures on the Borel sigma field in this space. Let us recall that this quantity is well known as a model of continuity of the function x. Let us introduce this notation. So for function x, which belongs to space C01, let us define new function omega x delta, which is equal to sup over t2 t1 minus t2 less than delta. Here is x t1 minus x. So this is just maximal difference of the value of this function when values of argument are not very far one from another. And this omega is called a model of continuity of function x. And it is evident that it must go to 0 for any function x because of this, because we know that any function from here is equicontinuous, uniformly continuous on the interval 0, 1. So this is a model of continuity. And it is evident that x delta tends to 0, delta tends to 0. And characterization. Compact we already wrote that is the following, that this quantity must go to 0 uniformly on our set A. From this one can get the conditions of weak compactness of the family of probability measures. So let us now consider the family. Let us now consider the family mu alpha probability measures on C01. Then it is weakly compact. Let me formulate it as a theorem. Mu alpha is weakly compact. Weakly compact. And only if again we have two conditions. One comes from the idea that compact set must be bounded. So the first one. Let me write it in slightly different case. You will see that this is the same, but okay, let it be theorem 0. If the sub over alpha belongs to set of indices of mu alpha of such x that norm of x is greater than r tends to 0 when r tends to infinity. And second one, is the following. Let me. The sub over alpha belongs to A. Here is mu alpha of such set of x that omega x delta is greater than epsilon. Okay, greater than epsilon tends to 0 when delta tends to 0 for any epsilon greater than 0. Of course, I can write it in the same way as before for Hilbert case, saying that for any epsilon there exists delta 0 such that this is less than epsilon. But it is of course the same, so it is not necessary to rewrite. So we have this relationship, and again they are related to different possibilities for probability measure to disappear. One, keep these measures in some ball. Another one, do not allow these measures to go to, we can say coordinates, but this is a very serious notion in C01, but to infinite subspaces. Yeah? So we have these two conditions, and now let me note to you that this condition can be related to second one, and this condition can be made slightly weaker. Why? Let me write you a picture. We have for example, we have the continuous function of 0, 1. Here is its graph. Then I insist that if we control omega, this is f, if we control omega f delta, for example, we know that omega f delta is less than some x. Yeah? Put here delta 0 epsilon 0. Then I can control norm of f just using initial value of f of 0, or maybe a value in some other point. It depends, by the way, on the problem. And this quantity. How? I say that this is less or equal than, here we just use absolute value of this one, plus, and what we will put here, epsilon 0 multiply on 1 divided by delta 0, maybe plus 1 for 2. So this is inequality. Yeah, this is inequality. It is evident how to get it. We just make a partition of interval 0, 1 by the intervals which has the length less or equal than delta, and then one can check that any difference between two values here is less or equal than epsilon 0. So we can go from this value at maximum on this quantity. Yeah. So this trivial inequality. From this point of view, one can substitute condition first in our theorem 0 by the more convenient condition. So condition 0 will be substituted to condition 1 in right statement about weak compactness in our space C01 as follows. Let us say that sup over alpha belongs to set of indices A alpha. Excuse me. Here is mu alpha from the set of x such that the value of x at the point 0 is greater than r. Yeah, goes to 0 when r goes to 0. Okay. So we have now a statement about the characterization of weak compactness in the space C01. And from these two examples, Hilbert space and C01, we understand how to get the characterization of weak compactness in arbitrary Banach space. What we have to do? We have to find characterization of the compacts and modify this, applying this sup over all mu alpha from our family. That's all. These are the idea. And now I want to illustrate this idea to you on using a very famous example of the weakly convergent family of random elements in our space C01. Namely, we will consider the construction of the Brownian motion as a weak limit of the some processes, constructed from small perturbations in the space C01. Let us try to do this. So even it can be named invariance principle. What we will consider? We will consider the family of independent Bernoulli random frames. Independent and epsilon k is equal -1 and 1 with probability 1. Then I will choose, I will consider the following sequence, like Sn is equal to sum from k equal 1 to n epsilon k. How it can be interpreted? It can be interpreted as follows. We just have a point which is placed in 0 on our real line. Then at any moment, any natural moment of the time, it gets some pushing to the left, to the right, randomly, and this point became move like this one, and maybe so. This is a well-known symmetric random walk as our real line, and it is a model of the motion of the particle which is originally placed there under the just interaction with the molecules of the media. This is a well-known model, and we already expect that when we do appropriate scaling of the time, now time is n, and space, now space is measured by this 1 and -1, then one can expect that this random walk will approach some continuous in time, at least process. And it is true. In this way, one can get the mathematical model of the Brownian motion in one-dimensional case. Let's try to do this. So, first of all, let us organize the appropriate process with continuous time from this one. How I will do this? I will consider for fixed n the set of these partial sides S put as 0 equal to 0, S1, so Sn. Then I will take such points in the coordinate plane for every k equal 0, n. Consider point k over n, sk over square root of n. Here is the point. And then construct the random element psi n is polygonal line. With this vertex, with vertices k n s k square root of n, and in the picture it looks like this. We have a partition here above, and we just go in this way. Here is psi. Our aim is to check that psi n weakly converge. Is to check that psi n converge in distribution. Well, first of all, let us check that psi n are weakly compact. Let us start to do this, and firstly check that they are weakly compact. So I will not check all this statement, but I will begin with the slightly weaker statement that psi n as a family of random elements C01 is weakly compact. Then let's see what we can check. The first one. Psi n from 0 always is 0 for any n into the 1. So this condition holds trivial. The second one, what we want to discuss. We need to discuss the following. We need to discuss the following probability. The probability that omega psi n theta is greater than epsilon. So we need to discuss the following. Then let me note that instead of beta, I can use some only rational numbers, and due to the structure of our random function psi n, this probability can be rewritten as follows. This is the probability that here is the maximum k1 divided by n minus k2 divided by n is less than beta. Here is the sum from J equal to K1. I will suppose K1 here is less than K2. To K2 1 over n epsilon J is greater than epsilon. Okay. And what we will do further, we will try to estimate this. Function, this probability. It seems that one can apply some inequalities related to the sum of independent centered random variables. So this is the next step, and unfortunately we did not succeed to do this step right now on this lecture, but this lecture is the last one in the semester. So our plans are following. We will have an exam at January 13, and at January 12 we will have some preliminary discussions in the morning at 9 o'clock in Kyiv time. So on those meetings at January 12, we will finish the proof here. Okay, today this is all what I wanted to say. Thank you for attention. Maybe somebody have questions or comments. If not, then I wish you a happy new 2023 year. Best wishes and bye.